So do you have any questions from the previous class? Any questions? No. Okay. So let us start. So note down one theorem. If three forces acting in one plane upon a rigid body at different points, of it be represented in magnitude, direction, and line of action. As I told you earlier, so these are the three important properties of any force. And line of action. By the sides of a triangle, taken in order, then they are equivalent to a couple. Whose moment is equal to twice the area of the triangle. Now here actually there are three different forces that are acting on a body. So three different forces are acting on a body, but all the forces can be represented on a triangle. Now, so this triangle be this particular format, let us say. So there is one force, this is P, and another force, this is Q, and another force, this is R. So there are three different forces that are acting on a body, and all the forces can be represented like a triangle in a plane. And this triangle represents the force magnitude, direction, and line of action. So this is one force whose magnitude is of magnitude P and acted along the horizontal direction like this, and the line of action actually is on this particular line. The magnitude and the line of action, so both were shown here, and the direction also is inherent. Now similarly, Q is the magnitude like this, and R is the magnitude like this along with the direction and line of action. Now here actually, so these three forces actually, can I say that these three will form a resultant of 0? Yes or no? Can I say that? So here actually there is one fundamental understanding. So it may or it may not form the equilibrium case. So why? Because see this, the three forces that are acted like this, right? So three forces are represented on a triangle. So three forces are represented on a triangle. So this may be more, this may be less, this may be less. So in that case, actually there will be certain resultant where actually I will give some problems where the resultant may not be zero. I am going to give such kind of problems, though actually they can be represented on a triangle like this. Now actually, triangular law of vector addition, what it says is, if three forces can be represented on a triangle, then the system is under equilibrium condition, or actually then there is no resultant force if all the forces can be represented on a triangle. Now here actually, on a body, these are the force magnitude that are acted on the body. It may not form the equilibrium condition. Got it? So the force magnitude can be represented like this, forming a triangle. So this is how actually there is one line of action, actually force that is acted on a body like this, and it is having a magnitude of P, and there is one more force that is acted like this, and then it is forming a magnitude of Q, and like this actually R is also formed. Now all the forces acted on a body, it may not form a triangle, closed triangle. Got it? But actually the force magnitude, whatever here we have represented, right? So this is forming a triangle. Got it? So now here actually the theorem, what it says is, if three forces are acted, so you can read the statement, three forces acting in one plane upon a rigid body at different points of it be represented in magnitude and direction and line of action by the sides of a triangle taken in order, then they are equivalent to a couple whose magnitude is equal to twice the area of the triangle. Got it? Twice the area of the triangle. So that means if the area of the triangle is A, then the movement of all the forces together, M is equal to 2 times of the area. So that's what actually the theorem says. So provided if the forces can be represented on a triangle like this. Got it? Now here, so to solve this problem, what we can do is apply two different forces at point A. So let us say this is point A, and this is point B, and this is point C. Now one more force, actually same magnitude, applied exactly at the same location, so that these two will cancel out, and then it will have no effect on this particular body, and this is P and this is the P. So P and minus P, so that no effect on this particular point. So I have explicitly put these forces. Now if you notice, at the point A there are three different forces, that is P, Q and R. Together will form how much? What is the equivalent force of this P, this Q and this R at this particular point? It will be 0, because at single point actually three different forces are acted upon. Now actually earlier, as I said earlier, this triangle actually, suppose if there is a body like this, on this particular body, one force acted like this, and one force acted like this, and one force acted like this. Now these three forces actually, we formed a triangle like this. This versus, there is one force that had acted on this, there is one more force that is acted like this, and there is one more force acted like this. Now what is the difference between these two? Here actually there is a single point where all the forces are acting. Now this is P and this is Q and this is R. Now here also this is P and this is Q and this is R. Now all the forces are acting on a rigid body like this, but here all the forces are acting at a point. Now if this forms a triangle, definitely the system is under equilibrium condition. Here actually, if these three forms a triangle, so it may not be under equilibrium condition. So it is subjected to certain conditions, whether it is equilibrium or not. Right? So that's why actually these three forces also forms the triangle. These three forces also forms the triangle, but this is under equilibrium. This may not be under equilibrium. Got it? Now actually here at point A, so at point A, the three forces P, Q and R, will be under equilibrium. Got it? So this is the main difference between initial triangle versus at this particular point. So initial triangle represents this and this point represents this. So this is under equilibrium. This may not be under equilibrium. So it will result into certain couple. So that's what actually we are going to derive now, right? So at this particular point, so this force and this force, all the three forces together will be under equilibrium. Hence, no resultant will be there for all these three forces. But there is one force here and there is one more force here which is separated by a distance of AB. Now these two actually are parallel to each other and will form a couple. Got it or not? So this one and this one will form a couple because these two are the parallel forces and their line of actions are different. So one is acting at this point and another is acting at this point and both are in opposite direction. Hence the P and minus P and minus P will form a couple of moment M. Got it? That M should be equal to twice the area of this triangle. That's what we need to prove. So you note down this, we are going to prove that. I hope everybody understood this concept. Okay, great. So now actually we will calculate the moment of this particular couple. Now the moment of the couple P and minus P will be M equal to, obviously AB cross P is the moment. So AB is the distance between the couple and then the force magnitude is P. So AB cross P is the resultant couple. So AB is a vector and P is a vector. So this moment actually we will be calculating. We don't worry about the direction of this particular moment. Why? Because whether it is clockwise or anti-clockwise, it doesn't matter for us. So what we are interested in is whether there is a couple moment or not. That's all. So here actually AB cross P. So AB is this height and P is this one. Now this can be expanded as the magnitude of AB into the magnitude of P and the angle between them, sine of angle between these two. Now actually when we are calculating the angle, so this is AB extension and this is P direction. Now the angle between them is this one. So this angle, suppose if I say this angle is theta, then this angle will be pi minus theta. So sine of angle between these two will be pi minus theta, not the theta. So sine of pi minus theta. Now this can be treated as AB magnitude into P magnitude into sine pi minus theta will be sine theta. Now here P actually I will keep it separate and then AB sine theta. So AB sine theta is nothing but the height between the bottom side and the top corner. So this is AB sine theta is the height. So this is the height. And P magnitude is this side length. So this is BC. So BC into, I call this as point D, BC into AD. Now BC into AD, if I multiply by 2 and then divide by 2, and this is going to be the area of the triangle. Got it? Understood? Or do you have any questions on this? Any questions? Why? Okay, so let me clarify. So Ramesh, so your question is only take AB, why not AC? So we have taken AB and not AC, right? So here actually we have made this as the equilibrium point by attaching three different forces. Now actually, if I want to eliminate the forces at this particular point, I have to consider P, Q and R, right? P, Q, R actually it will go off. That means there is one force that is acted like this and there is one more force that is acted like this, right? Now even here also, whether you take AB or AC, it doesn't matter. So even if you take AC also, you will end up with the same result. Because AC sin theta, now theta will be this one. Suppose if you take this as phi, then finally what you are ending up with is only the triangle area only. So this is going to be, AC will be, this is phi minus phi. The same answer you are going to get it. Got it? Ramesh? Okay. So one more doubt. Distance between the forces, Jakir. So what is your question? Should be perpendicular distance. So the perpendicular distance we have calculated, that is this perpendicular distance. For that purpose only, we have used this particular vector to calculate the perpendicular distance. Finally, we left with only the perpendicular distance AD only. Understood? Yakir. Okay. So any other question? I hope everything is clear now. Okay. So note it down. Okay. So note down one more problem. So this is a theorem. So as and when three forces can be represented in a triangle but acted at different points of the body, then so the resultant can be treated as if like a couple which is acted at two different points, equal forces, and the magnitude of the couple will be twice the area of the triangle formed by those three forces. So note down one more problem. Three forces P, 2P, 3P act along the sides AB, BC, CA. Act along the sides AB, BC, CA of an equilateral triangle ABC. Of an equilateral triangle ABC. Find the magnitude and direction of the resultant. Find the magnitude and direction of their resultant. And find also the point in which its line of action meet the side BC. And find also the point in which its line of action meet the side BC. Now here actually three different forces acting along AB, BC, CA. So this is A and this is B and this is C. So AB is acting in this direction but a magnitude of P, and BC is acting along this direction but a magnitude of 2P, and CA is acting like this and a magnitude of 3P. Now actually can we say that these three forces will form a closed triangle, right? So can we say that the system of forces are under equilibrium condition or not? Can somebody answer my question? Whether the three forces together, is it under linear equilibrium or not? Not even the circular equilibrium. Anyway, it is not under circular equilibrium. I am asking whether this system of forces will form a linear equilibrium or not. Will it have certain resultant or it will make a zero resultant? This is a big confusion. There is a resultant, right? So though it is forming a triangle, though it is forming a triangle, there will be an associated resultant with it. Why? Because just imagine this way. So there are three different frames or iron frames, or actually iron rods are jointed like this. On this joint, there is a 2p force acting like this, and 3p force acting like this, and 1p force acting like this. Now, definitely there will be a movement for these particular forces, right? Because actually these are not under equilibrium condition. But the forces, if you are able to form like a triangle, then actually, so the forces acting on a triangle here. But the no force magnitudes, if you are able to form as a triangle, then they are equilibrium. But the forces are acting on a triangle, it may not be under equilibrium. It may or it may not. I hope you got the clarity on that. Got it? So now in this particular case, so you first find out what is the resultant of these forces, and the second one is the line of action of the force. Resultant of the force and the line of action of the force, from where actually it is passing through, the resultant. First you tell me what is the resultant of these forces together. This is simple vector sum. Done? Anybody? Just the resultant I am asking. The line of action anyway I am going to calculate for you, but you please tell me the resultant of all the forces together. So let me explain this. See this. So if there are two simple forces, actually we will straight away calculate the vector sum with the help of triangular law of vector addition or the parallelogram law of vector addition. So if there are more than two forces that are acted, then actually the best way is to calculate by resolving into the perpendicular components. That is, suppose I will give you different forces like this. Now this is one force, and this is one force, and this is one force, and this is one force. Now actually, if you want to find out the resultant of all the forces together, one way is to find out the resultant of these two, and then for the resultant, you calculate the resultant from this, and then whatever the resultant you are going to get again, that resultant you have to find out the vector sum with the third vector. So the next vector, so that you will be able to find out the resultant. But this is much more complicated, right? So rather than that, the standard method what we follow is this vector we will divide into horizontal component and vertical component. If this is F1, then this is F1x and this is F1y. Similarly, if this is F2, then actually you divide this into horizontal component and the vertical component. Horizontal component will be F2x and vertical component will be F2y. Similarly, in this one only F3y is there, and this one the horizontal component, that is F4x and then F4y. Now the sum of all the horizontal component will be x is equal to F1x plus F2x plus F3x plus F4x, and similarly y is equal to F2x, F1y plus F2y plus F3y plus F4y. Now this is the entire horizontal component and this is the entire vertical component. Now this vector, the resultant can be treated as xi plus yj. So this is the resultant vector. So this is in the coplanar. So as I told you, though I am not specifying, we are working with only the coplanar forces always. So here xi plus yj. So xi plus yj is the resultant. Now from this actually you can calculate the resultant magnitude will be square root of x square plus y square, and the resultant angle will be theta is equal to tan inverse of y by x. So this is the standard method what we are going to follow in case of multiple forces are present. Now here also we will do exactly the same thing. So this is the horizontal component of the force. So this is only in the horizontal direction and is having a magnitude of 2p. And this vector, I will divide this into the horizontal component and the vertical component. This is the vertical component and this is the horizontal component. So horizontal component will be, so this is an equilateral triangle what he has given. Then this angle will be 60 degrees, this will be 60 degrees and this will be 60 degrees. Obviously, so this angle is 60. So obviously this will be P cos 60 and this is P sin 60. So acting downwards. Similarly, this particular force which is acting upward, so the horizontal component will be 3p cos 60 is the horizontal component like this, and the vertical component will be upward in direction. The magnitude will be 3p sin 60. So if you add all the forces together, the x will be, so horizontal, this right side actually will always treat the positive x direction. So this is the positive x direction, this is the positive y direction. Hence x is equal to 2p, which is the base force which is acting horizontal, and then this particular force is actually one vertical component is there and one horizontal component will be there. We are interested in the horizontal component now because we are calculating the resultant x, and this is aiding this there. So that means this is opposing. So this is actually opposing in nature because actually this is a downward force. Downward vertical component and left side horizontal component will be there because this is the resultant of it. So this one will be minus P cos 60. And this will be, so this is having one vertical component upward direction and this is also the left direction component will be there. So because this force, right, so this can be divided into this component and this component. So this is again the leftward, that means minus x direction, and this is also minus x direction. So this is also minus 3p cos 60. Now this will be minus 4p cos 60. So this is equal to 2p minus 4p cos 60. 2p minus 4p into cos 60 will be 1 by 2. So 2 will cancel and 2p will cancel, and then hence no vertical resultant. So no horizontal resultant. So x will be 0. Now actually y we have to calculate it exactly in the similar manner. So y component will be, so for this component there will be a downward vertical component of magnitude sin 60, that is P sin 60 in the negative direction minus P sin 60, and one positive component because of 3p which is in the upward direction, that will be sin 60 plus 3p sin 60. Sin 60 will be root 3 by 2. So 2 times of p into sin 60. Sin 60 is root 3 by 2. So this 2 will cancel out. Root 3p is the y component. So the resultant vector will be r is equal to root 3p into j, or the j. So this is the resultant vector. Got it? So this is the resultant vector, which is nothing but, it says that only j component is there. That means the angle of action will be tan inverse of y by x will be infinite. So tan inverse of infinity will be pi by 2. That means this is acting vertically. So no horizontal component, but there will be associated vertical component. But that vertical component may be here, or maybe here, or maybe here, or maybe here, or here, or here. We don't know. Now the next part of the question is, where is the line of action of the force? So this is acting vertically, but where? That is the question. Got it? So from this actually all the three forces together is having a resultant of magnitude root 3p, which is acting vertical. Vertical means vertical can be anywhere, but what is that place? That is the next level of question, right? So that is the line of action of the force. We have to calculate it. First we note down this, we are going to calculate the line of action. So now actually, how to approach the line of action? How can we find out from where this line of action is passing through? What is the basic idea behind it? So in the problem statement, what he said was, so at what point of BC the line of action is passing through? What is the fundamental idea behind that? So the fundamental idea behind that is, now actually yesterday I have proved one theorem. If there are multiple forces that are acted on a body, then if you find out the moments of each and every force about any random point, and the sum of all the moments should be equal to the resultant of all the force moment about the same point. So this is actually one theorem I have proved yesterday. Now we will use exactly the same theorem. And one more important aspect is, if the force is passing through a point about which, if you are interested to find out the moment, then what will be the resultant moment? So what I said was, so about this particular point, actually I wanted to find out the moment of a force which is passing through it. So this is F. I wanted to find out the moment of this particular force about this particular point O. What will be the moment of this force about this point? Can somebody give me the answer for this? What will be the moment of this particular force about this particular point? Will be, as I said, so as Anubhav said, so this is 0. Why? Because, so when we are calculating the moment, we have calculated the force getting multiplied by the perpendicular distance from the point about which we wanted to find out the moment. That means, suppose if this is the point and this is the force that is passing through on the particular body, about this particular point you wanted to find out the moment of this force, then what you need to do is just draw a perpendicular. Foot of the perpendicular has to land on that particular force, and then this length getting multiplied by this force will be the moment. Now when the force is passing through the same point, then the perpendicular distance from the point will be 0, because it is passing through the point. So hence the moment of this particular force will be 0. I hope everybody understood this. So here actually the moment is not equal to 0, and here the moment is equal to 0. So I hope everybody got the clarity on this. So the moment is nothing but the twisting force about this particular point. So if I want this force, actually if there is a body like this force will cause the body to move in this direction. Now here actually this particular body, now about this particular point only it is passing through. That means about this particular point there won't be any rotation like this. Hence the moment will be 0. Right? So now actually for this particular one, there are 3 different forces that are acting on this particular body, and all the forces together will have a definite moment. And if the resultant is passing through certain point, let us say this is one particular point on BD, this is one particular point on BC. So let D be a point on BC. Then if the line of action, so line of action we mean here the resultant. So if the resultant passes through the point D, then the moments of all the 3 forces about D will be equal to 0. So this is since the resultant passes through this. Since the resultant passes through it, hence the the moments about that particular point D for the resultant of all the forces is equal to 0. Here actually, here the assumption what we made is, that is a correct assumption, the resultant of all the forces together actually we calculated it to be root 3 times of P. And root 3 times of P, it may pass through like this, it may pass through like this, it may pass through like this, it may pass through like this. Now actually we are assuming that it is passing through D. So if the resultant is passing through D, then the taking moments about the resultant for this particular about D will be equal to 0. Obviously, root 3P is passing through this with an angle of 90 degrees. Like this actually it is passing through. Got it? For this particular force about this particular point, the moment will be 0. And based on the theorem, there are 3 different moments. And whose resultant force is this one? So taking the moments of all the forces about this point will be again equal to 0 because this resultant is passing through this. That's what we are going to do it now. So M1 plus M2 plus M3 equal to MR is equal to 0. So this is the resultant, MR. So M1 is nothing but this particular force. So this force about this particular point, I wanted to calculate the moment. Now how can I calculate the moment? For this particular force about this point, I wanted to calculate the moment. How do we calculate the moment? Can somebody tell me how we can calculate the moment of this particular force about this particular point? So moment is nothing but the torque. So this force actually, if it is applied on a body like this, then actually in which direction it will try to move? With what magnitude it will try to move? So that's what is nothing but the moment. So we have calculated R cross F and that was proved to be the force getting multiplied by the perpendicular distance from the point to the force. So that's what is the moment, right? I hope everybody understood that fact. So if you want to calculate the moments of this particular force about this particular point, then draw a perpendicular from there. So this is the perpendicular. Yeah. So draw the perpendicular like this, and then this length will be the perpendicular distance. So we have to calculate the moment M1 as the force P getting multiplied by, suppose I call this as S. So I call this as S. So then ds, P getting multiplied by ds is the moment of this particular force about this particular point. Now, if I want to calculate the moment of this particular force about the same point, again I have to draw a perpendicular landing on this particular force. So here actually, even if I draw from here or here or here or here, anywhere if I take it, I cannot find out a perpendicular for this particular force to this particular point. So in that case, what you need to do? You are interested only in the perpendicular distance. That means you can extend like this and then try to draw a perpendicular from there. So this is what is interested for us. So if I call this as S, then I call this as T. So this point is T. Now dt is the perpendicular distance. I hope everybody understood that. Understood? Okay. So dt is the perpendicular distance. So for M3, what I will do is, for M3, the force magnitude is 3p and the perpendicular distance is dt. So here actually, ideally, the way we can do is, you do a cross, so cross product of this 3p getting multiplied by this distance. So that is going to give the same magnitude. So cross multiplication of r with the same force will give a perpendicular distance because r sin theta. So to simplify our process, so in the calculation of statics, we always treat the perpendicular distance as if like it is r cross f. Got it? So finally we are doing only the r cross f. But in r cross f, we will be extend f into r sin theta. That r sin theta is the perpendicular distance. So as and when we calculate the moments, we are always taking the perpendicular distance straight away, so that I can do a scalar multiplication here without worrying about the vectors. So r cross f will be complicated, but f into some magnitude of radius will be obviously scalar multiplication, which will be very, very easy to understand. So that's why perpendicular distance with a scalar multiplication of the force. Ideally, it came from R cross F. In R cross F, R sin theta is the one which will nothing but the perpendicular distance. So the moments are only the vectors only. Finally, though you are doing the scalar multiplication here, so this has to be treated as a vector whose direction is perpendicular to both the radius and the force vector, which is nothing but the perpendicular to the plane of this particular forces. So as I said earlier, right? So torque is nothing but a twisting force. When we are talking about the twisting force, the direction will be, so many people will get confused. Now actually suppose if I take this particular point like this, and this is a rod. On this rod actually I have applied a force like this, right? So this is at a distance of R. Now if I apply a force like this on this rod of radius R, then this will try to rotate like this, right? If it is rotating like this, then what is the direction of the torque? What is the direction of the torque in this particular case? So this is a big confusion. So this is R and this is F. Now actually, so R and this is F. From R to F actually this is the anti-clockwise moment we take it. The anti-clockwise moment we take here actually this is R cross F. What we are calculating is the magnitude as R cross F, and we say this is an anti-clockwise. Now the direction of the torque, we always say the axis which is perpendicular to this particular board. So that is the torque direction. So about which axis actually the force is resulting in a twisting moment. That axis direction we call as the torque direction. So whatever the moment we calculate here is nothing but the torque. Torque is nothing but a vector quantity. A vector actually it is representing a perpendicular vector to both radius and the force. Got it? About which actually this force is trying to rotate this radius like this. Hence, the axis is coming outward. We treat as positive in case of anti-clockwise direction. Suppose if the same force is acted from this side, then actually it will try to rotate in the clockwise direction. In that case, the axis we treat as going inside to the board. So, this is always a vector. So, here actually, suppose if this force is acting like this, then this is F direction, this is R direction, this is angle theta. So, this is angle theta. And this is again in the anti-clockwise direction. But what we are interested is this perpendicular distance, because if this angle is theta and this is R, and this value will be R sin theta. So R sin theta. Here actually R cross F is nothing but R into F into sin theta. So we treat this as R sin theta into F. So this is nothing but, so this perpendicular distance R perpendicular into F. So this is what we treat this as the torque or the moment. So this moment direction actually is always, if it is anti-clockwise, then actually we treat as the positive direction, which is nothing but coming out. And if it is clockwise, going inside is the axis of rotation, which we treat as the negative. So even here also, here actually this is the, so here actually this is the point of calculation or about which we wanted to find out the moments. Now this force actually is having a radius like this, and this too will result into a moment about this particular point, and that moment will be this length, which is nothing but the perpendicular distance getting multiplied by this force. So that is the moment. Even here also, this is the line of action of the force, and this is the perpendicular distance about which this point is getting moved, and then we have to consider the sign also. Then finally we will be able to calculate the moment of these forces. Now there is one more force which is nothing but this force, horizontal force. This is passing through the point D. Then actually what will be the moment of that particular force? Moment of the force BC. So this will be 0. We don't need to consider this particular force because the moment is anyway 0. Now here actually for taking care of this sign, here actually, so this is the force direction and this is the radius direction. Then from R cross P, R cross F. So this is actually anti-clockwise, sorry, this is anti-clockwise direction. So this anti-clockwise direction we can treat as the negative. Now here actually this is the force going in this direction and this is the radius direction. From R to F, this is the direction. This is the clockwise direction. So this is clockwise direction, this is anti-clockwise direction. If you treat this as negative, positive, then you can treat this as negative. If you treat this as positive, this you need to treat as the negative. So it doesn't matter whatever the convention you follow, you need to mention that. Clockwise is positive or negative. Got it? So here we need to consider. So this actually anti-clockwise I take as positive and clockwise as negative. So this is minus and this is plus and this is 0. Got it? So now actually P into ds minus 3P into dt. So ds actually we can express into the known values. So ds is nothing but this distance. This is so this is BD and BD cos 60 sin 60. So BD sin 60. Minus 3P into dt. dt is this distance. This distance actually we know this angle as 60 degrees and this angle will also be 60 degrees because alternate angles, sorry, opposite angles. So this is 60 degrees and this is 60 degrees and this length is nothing but DC. So DC and DC cos 60 sin 60. So DC sin 60. So P into BD sin 60 is root 3 by 2 and here also sin 60 is root 3 by 2. Root 3 P by 2 if you take it out, so BD is left over here minus 3 times of DC is left over here. Yeah, so BD minus 3 times of DC. BD is this distance and DC is this distance. So this can be treated as BD can be treated as BC plus DC minus 3 times of DC. So BC minus 2DC root 3 P by 2 BC minus 2DC and this is equal to 0. So we started with that assumption, this is equal to 0. So because the resultant is passing through that particular point. Now if this is equal to 0, BC equal to 2 times of DC. BC equal to 2 times of DC. That means DC is equal to BC by 2. So this is at a distance of DC which is given by 3 times of BC by 2. Got it? Understood? So if you express in terms of BC and BD, then BD equal to DC equal to BD minus BC equal to BC by 2 or BD equal to BC plus BC by 2 or 3 by 2 times of BC. So you can express in any of the manner. Both are correct. Understood? Okay. So this actually, if you are able to understand this particular problem, you will be able to solve most of the problems from statics, because actually all the concepts are based on only this understanding. One is the calculation of the moments and the calculation of the resultant force. The methodology is same and the complexity increases with the number of forces, that's all. But the process is exactly same, whatever may be the kind of problems what we are going to solve with. So here actually if you notice, the complexity keeps on goes only with the number of forces and the direction of the forces, but the understanding is same. So what we are interested in case of statics is finding out the equilibrium of the body. So equilibrium means only two aspects. One is the linear equilibrium, another is the rotational equilibrium. linear equilibrium. So we have to assure that the sum of all the individual forces to result into a zero. So that is one aspect where there is no linear moment. And the sum of all the moments, if it is equal to zero, then there is no circular moment. Hence, the body is under circular equilibrium. So if both are satisfied, then we say that the body is under equilibrium condition. Got it? So what is the previous class theorem you are referring to? Force is equal to the couple. So I didn't understand your question, Anubhav. So here actually resultant is not passing through the center, right? Center of the triangle, right? We cannot do that way. So in the previous theorem, actually what we have talked about is if the forces can be represented on a equilateral, so on a triangle like this, right? The forces can be represented on a triangle like this. In that case, actually we can apply. Here actually the structure is in triangle format, but the force magnitudes are different. Yeah, force, yeah. So how can you apply that theorem at this particular case? Here actually, earlier theorem what it says is there will be a couple that is resulting provided if the forces are under linear equilibrium. So then only we can apply that theorem. Here actually there will be certain resultant that is left over here. Hence actually we cannot apply. That's what I say, right? So earlier actually when we dealt with, right, all the three forces together at this particular point, if it is making an equilibrium, then we will be able to do that. But it is not making an equilibrium here. Got it? Understood, Anubhav? Here actually, when I start this problem, I have given one important point. That point is, so if three forces, their vectors are forming a triangle, closed triangle, then the resultant will be zero. In such case, you can apply that theorem and try to solve it. That is one way. But here in this case, the structure or three different rods are located like this, but different magnitudes of the force that are acting on this. These three forces together may not be under equilibrium. So because the force magnitudes may not form a triangle here. Got it? So if the forces are under equilibrium, then actually you will be able to apply that theorem. But here the forces are not under equilibrium. Equilibrium meaning linear equilibrium. So here actually we have found that actually the resultant is not coming out to be zero. Hence you cannot apply. Yeah. Any other questions? Got it? So note down one more. As I said, this is a fundamental aspect where you should understand each and every point in this particular problem. So because whatever may be the number of problems we are going to deal down the line in the entire statics, we in and out, right? So we will be dealing only with the equilibrium. So that is the resultant has to be equal to zero and resultant moment has to be equal to zero. So this is a straightforward and simple problem. In one step you will be able to do that. So this is three forces PQR act along the sides BC, CA, AB. BC, CA, AB of a triangle ABC. Taken in order. If the resultant passes through the center of triangle ABC, if the resultant passes through the incenter, incenter of triangle ABC, then prove that P plus Q plus R equal to 0. Yeah, so Jackie, your question is, regardless of the condition of either equilibrium or not, will the resultant moments be always 0? If there actually the statement is not complete. So that will always be 0 provided if you take a point where the resultant is passing through it. So taking that point as the reference about that particular point, so the moment will always be 0. Got it? So whether it is forming a equilibrium or not, it doesn't matter. If you take a point or if you identify a point where the resultant is passing through, about which the forces will make a moment of 0. So then only the statement will be complete. Yeah. So can you prove this? Anybody got the answer for this? Three forces PQR act along the sides of a triangle BCCA of a triangle ABC taken in order. If the resultant passes through the incenter of triangle ABC, then prove that P plus Q plus R equal to 0. This is actually, you can straight away make out. So here actually A, B and C. Now incenter is nothing but a circle actually which is drawn by touching all the sides of the triangle. Now actually the intersection will be angular bisectors will make the so this one is same and this one is same and this one is same, right? So this is the incenter. Now incenter, obviously if it is touching the side, then you can draw a perpendicular from there. So this is the perpendicular drawn. Now the perpendicular is nothing but the in radius R, obviously. So because the circle is touching from the center, if you draw a line to the tangent, that will be perpendicular to that. So that line length will be the radius. Now as the resultant is passing through the incenter, so resultant of all these three forces, so AB, BC, CA is passing through. So AB, there is a force that is acting on this of magnitude P and on this magnitude Q and on this the magnitude R. Now these three forces is making a resultant. We don't know the magnitude of that, but we know that it is passing through the incenter. Now if you take the moments about this particular point, then the resultant moment will be 0 because the resultant is passing through this particular point. And that has to be equal to the sum of individual moments. So by taking the moments about the incenter, then the resultant moment will be 0. As the resultant passes through it. So therefore M1 plus M2 plus M3 is equal to 0. Now M1 is nothing but P into the perpendicular distance. So this is a perpendicular, this radius itself is the perpendicular. P into R plus Q into R plus R into R is equal to 0. Now if you take the radius out, P plus Q plus R times the radius is equal to 0. It implies P plus Q plus R equal to 0. Got it? Understood? Now the similar kind of problems actually you can solve many. So I am going to give you an assignment on this. So first we will solve this, then actually we will go to a little complex level, that is not the three forces, we will go to the multiple forces. Many forces, coplanar forces are there. Then what will be the general condition for the equilibrium? It is same, but actually we will go in a systematic manner. So the same procedure we will be adapting in a systematic manner. So to multiple forces. Here actually today's discussion is just limited to only the three forces. Now what if there are 100 number of forces, 200 forces? Then actually how we are going to deal with this kind of cases, right? So on this kind of problem what we have solved now, I am going to give an assignment today, and tomorrow actually I am going to deal with multiple forces. Got it? Any questions you can let me know now. Any questions? Yeah. So that's all for today. Yeah. Thank you. Good night.